Welcome back to the latest lecture session. In the last couple of sessions, we were talking about trying to remove the suspended solids from drinking water. We were measuring that by turbidity, and the principle was forming bigger particles by destabilizing them and then letting them form flocks, the bigger particles, and then we use sedimentation to settle them down. Even after this, there will still be some particles that are still suspended or will take much more time to settle down in a sedimentation tank, right? So what are we going to do next? We are going to look at filtration. So let's move on and look at filtration. So what have we looked at until now in water treatment? Let me just put it up. So preliminary treatment in the terms of core screens or such, and then we are going to look at coagulation and then flocculation, right? Destabilizing the particles, forming flocks, and then sedimentation, right? Flocculation here. So filtration is next. I am going to filter the particles out. So that's pretty straightforward. And again, what's the primary purpose? We are always trying to remove the suspended solids, different sizes of suspended solids. So why can't I, let's say, remove this sedimentation and directly have filtration? Well, you will choke your filter. Maintenance can be high, head loss will be high, but I think we will discuss this in today's session. Let's get this started. Filtration, I guess typically when we think of filter, we'll think of, let's say, this size, and let's say if my particle is bigger than this, then it's going to be trapped, right? This is like the plan view. I'm trying to say that this is the pore size or such, and this is my particle. But again, that's not the only way how filtration occurs here. Let's look at it. Again, what are we trying to do? We are trying to remove suspended particles so that the turbidity is what we want. I think turbidity was supposed to be less than 1, right? At least in Indian conditions. So let's get this done. So depth or sand filter. We have a sand filter. Okay, these are crude drawings, obviously. So water comes in. You have sand of relatively different diameter depending upon whether it's slow sand or rapid sand filter. Again, we will go back to that. So water comes in and particles are filtered out, and then water leaves the system, typically, let's say, depending upon where you have your water collection system here, right? So depth or the sand filter, depth filter, right? So that's what we have here, as in the filtration occurs over the depth. And then surface, where we use the microfiltration and ultrafiltration membranes. I think when we looked at the graph that illustrated the different sizes of particles, we looked at the different kinds of filtration mechanisms that can achieve the removal of those particles. In that context, I believe we looked at this microfiltration and ultrafiltration membranes. Again, these are based on filtration at the surface. We will look at this again. So, okay, this is, I guess, a graph that I was looking at. So, we have sand, we have silt. Again, we are looking at conventional filtration for now, right? So, I can capture some bacteria, yes, and cysts, silt and sand, and depending upon adsorption, maybe some of the other particles too will be removed. For example, NOM adsorbed onto sand or such, or let's say at least some particles of clay can be removed. But again, you understand the size in general though, but depending upon the type of filtration, you will be able to achieve, what do we say, until 0.1, but usually just above 1, that's a good enough cutoff for conventional filtration, right? 1 micrometer is the typical cutoff, though you will have some removal between 0.1 and 1, removal of particles between 0.1 and 1. In general, you can think of 1 as a cutoff, let's say. And 1 micrometer size particles are usually the hardest to remove by conventional filtration. We will look at this or come back to this aspect. And now, as you see, if I want to remove smaller particles, I need to look at microfiltration or ultrafiltration, and this is what we talked about, or when we say surface filtration, let's say, right? When we say surface filtration, it's based on the type of or the mechanism. So you have a membrane, and most of the filtration occurs on surface, or pores more or less which are not very deep, let's say, right? But with respect to the filtration using sand, the filtration occurs across the depth. So that's why we say, or the depth of the sand, that's why we say it's depth filtration, right? So that's something to keep in mind. Let's move on now. So, filtration mechanism, right, typically as we mentioned, one can think of it as if it's straining, right. My pore size is this big and my particle is this big, and so the particle will not fit through the pore size and it will obviously be filtered out. So, that is straining. So, that is but one mechanism of how particles are removed. We will look at the different mechanism. So, depth filtration mechanism, okay. As can be seen, we are going to look at adsorption, right, adsorption onto the media, and adsorption contact mechanisms. It can be by interception. Colloid hits the media due to motion of water. Let us say my particle is out here and the water particle is flowing near the relevant media. This is my media, and then the colloid that is coming along with the relevant water will be intercepted, let us say, interception. And diffusion, as in you have, what do we say, due to the thermal energy, the particles having their Brownian motion. Well, I guess I should not have drawn it like this, maybe something like this, and they can end up, what do we say, adsorbing onto the media. This is my media here, right, and this is how my particle can also be adsorbed onto the media. And sedimentation, as in if the particle is going through in this way, but because of the weight of the colloid or the relevant particle, it is going to come in like this, and it is going to have or it is going to undergo sedimentation, let us say, due to gravitational settling, right. So, sedimentation also can occur, but this is within the what do we say, filter, right. So, interception, diffusion and sedimentation. We will look at these aspects, but these are the primary aspects other than straining, right. We will look at these aspects. Okay, here we have a decent figure from water and wastewater engineering by Davis McKenzie, where you can see the relevant mechanisms being illustrated. Let us see what else we have. So, mechanical screening. So, that is what you have. Yeah, they are screened out. Why? The particle size is bigger than the pore size, let us say, right. And then sedimentation. Okay, you have this sedimentation, instead of the particle taking this flow path, let us say the settling velocity, such that in this case is that it will come out here and settle on the relevant particle. So, you see the sedimentation occurring out here, let us say. And flocculation. So, again, if the particles have been destabilized by flocculation, or pardon me, coagulation earlier. So, flocculation can take place even within the relevant media. So, the flocculation can be again, it is pretty representative here, but there are different kinds. It is not the only way that flocculation can occur, but particles can flock together or aggregate together or aggregate because of differential velocities due to either the fluid or the relevant settling velocities, right, and you can end up having flocculation here. And interception, right. So, this is what we have. So, water is taking the particle nearer to the relevant media, this is the media, and then you see that you have interception of the relevant particle on the relevant media, right. So, that is something that you see here. And impaction, well, I guess depending upon the velocity and the inertial forces, sometimes, and again this depends upon the weight of the particles too, they do not change direction with the flow of water, but they impact on the media, and that is how you are going to have what do we say, removal of the relevant particle. So, mechanical screening, sedimentation, flocculation within, interception and impaction, right. More or less we have covered this, but again as I mentioned earlier, Brownian motion too, but that will depend upon the type of what do we say, motion, I guess, right. This is typically for smaller particles, but we will look at this in detail, but this is a usually accepted overview of how particles can be removed. So, here we have another mechanism that clearly illustrates what I wanted to mention earlier. This is from Kittunen et al. So, what do we have here? You have the particle trajectory and the streamline here, right. So, what do I have here? This is the one with respect to Brownian motion. As you can see, particles always, I mean typically smaller particles anyway, in the context of filtration, you are going to have Brownian motion. Diffusion. So, in this random motion, the particles will come and what do we say, be adsorbed by the relevant media. This is the media obviously, right. And what else? So, again interception, I guess, in a way. So, the water is taking the particle near the relevant media and then it is intercepted. The other one is settling, rather than going out, not going out. So, because of the settling velocity of the particle, it is going to take this path rather than, let us say, the path of water out here, right. So, that is with respect to sedimentation, right. These are the aspects. So, if you look at it, I guess interception, diffusion and sedimentation, these are the three aspects that we mentioned, and depending on how you want to nitpick, you have other aspects coming into the picture. So, let me move on. So, depth filtration mechanism, okay. Now that the particle has been adsorbed, that does not mean it is going to be removed. Some of these collisions are not going to lead to, or not collisions, interactions, let us say, right, are not going to lead to removal. So, what am I concerned with? I am concerned with the effectiveness of the contact between the media and the relevant particle. So, fraction of the colloid and the media particles that result in attachment, right. Fraction of colloid media particles interaction that will result in attachment, depends obviously on effectiveness of coagulation. If the particles are very stable, we know, or we looked at some of the aspects that will prevent particles from being adsorbed to each other, right. So, we are not going to that aspect here, right. Models seems to be predicting that different types of contacts occur in a typical filter design. We will look at the data later. So, colloids will be removed when the significant fraction of these interactions or contacts result in attachment, right. So, again that is a different thing, it just means that not all interactions or contacts lead to attachment and removal. So, we talked about aspects such as removal by diffusion, removal by interception and removal by what else? Sedimentation. Let us see which, what do we say, kind of mechanism predominates at which particle size and such. So, here looks like you have transport efficiency and here we have particle diameter, right. So, influence of particle size and density on filtration transport efficiency. So, what do we have out here? So, here is the sum, this is the total if you want to look at it, sum 2. And as you can see, when the particle size is relatively lesser, what predominates? Diffusion predominates, and that is what you see in this zone. Particle size is lesser, then diffusion predominates, yes. And at the relatively higher particle sizes, what do you see? You see that you have sedimentation and then interception, right. Sedimentation out here and interception, again this is the sum, I guess, yes. So, sum of only these two and sum of all the particles. So, as you can see initially for very small particles, this is the sum with respect to removal efficiency, and then later again removal efficiency increases, and this part of the removal efficiency is due to interception and sedimentation. For bigger particle sizes, obviously as you can see, diffusion relatively lesser role, let us say, yes. So, again you can see that it is logarithmic scale here, that is something to keep in mind, right. So, let us move on. So, surface filtration mechanisms, screening, obviously this is what I mentioned earlier, or straining in a different or used a different word. So, when the particle size is greater than the pore size, obviously, right. So, here though I guess I should have pointed this out, we were talking about depth filtration until now, depth filtration. In the context of depth filtration, we looked at sedimentation, we looked at diffusion, we looked at interception, in general the principle based mechanisms, and if you are looking at what do we say, other aspects, we also looked at the other 5 mechanisms, let us say, right, which included flocculation and so on and so forth. Here this was with respect to depth filtration, but with respect to surface filtration, when we have the ultrafiltration or microfiltration mechanisms or membranes, what is the primary mode? It is screening. So, for screening to occur, what needs to happen? The particle size has to be bigger than the pore size, that is the primary aspect. So, that is what you see, this is the water coming in, relatively turbid water coming in, and here you have the relatively impermeable or semi-permeable membrane, right. This is my membrane, either the ultra or microfiltration membrane. So, the particles will be removed out here, and the water that goes through or filters through is called the permeate, and this is the reject, let us say, reject or concentrate. Why concentrate? Obviously particles are being removed here and relatively less particles are going through here, right. And then what is going to happen? Obviously the concentration of the particles out here or in this water is going to increase. So, that is why we are calling it reject or concentrate, let us say, right. Waste stream containing particulate matter, and this is the water or the treated water that we are looking at. Let us look at it in a closer detail. So, surface filtration mechanism, right, straining or screening, this is the usual way, and sometimes you can also have coating on wall by small particles. And another aspect is that, after time progresses, this straining leads to a case where these finer particles are trapped by the layer here, which we are referring to as cake. But in general, as you can see, the main aspect is screening, let us say, right. So, that is something to keep in mind. Again, this obviously, as you see, the thickness of the membrane, I think we have the relevant figures, it is not going to be very high, it is going to be pretty low, and obviously that is why we are talking about removal at the surface. So, surface filtration mechanism. So, with respect to when or how you will have the unit process of filtration fit into the bigger, what do we say, scheme of water treatment plant, we will see what are the ways. So, here is the usual way. When the turbidity is high, and it will vary, we know that we are going to add a coagulant so that we destabilize it, and then we are going to add a flocculation or not flocculation, create conditions or mixing conditions with respect to the G, so that your particles flocculate, and then you are letting them to settle down, and then I am going to send the water through. So, here we have multiple media filter, and then the filtrate or permeate, or I should not call it permeate, the filtered water is what we are using. This is the conventional one. But let us say when the water source is such that the raw water turbidity is not very high, right, it is not very high though, and here the case we are looking at is lakes or reservoirs, let us say, where the water is not moving, but it is relatively static, right, and there with the assumption that the turbidity is relatively low, turbidity of the water coming in is low, we are going to do away with this sedimentation step, and after flocculation you are directly going to have what is this, filtration. But one aspect to keep in mind is that even here if you remove sedimentation, what is going to happen? So, you have the much bigger particles which will be deposited here, or will choke up your relevant filter, right, very quickly. What happens over time? The particles that you are filtering out, they will be absorbed there, right. After some time you have to clean it, what we refer to as backwash. But if the load of the particles coming in is very high, and also even the bigger particles which can be removed have not been removed earlier with a sedimentation step, what is going to happen? You will have to clean this filter pretty often, because your head loss, right, you will have to have some pressure, and that pressure or the head difference between what is coming in and what is going out, the head loss will be remarkably high, right. So, that is one reason why you will usually have sedimentation prior to filtration, especially if the turbidity is relatively high. And again, depending on the source of turbidity, not source, the extent of turbidity or extent of the suspended solids, you are even going to do away with flocculation and just coagulation, and then you are going to have filtration, let us say, right. So, that is something in mind. Again, different version, but here we see that we have a roughing filter and then filtration. Okay. So, let us move on. So, granular media filtration, let us say. So, we are going to talk about the media here. So, granular media, we have the sand, typically sand, and then underlying layer of gravel, right, you can't have only sand, and you have the water coming in, or this is the standing water, you can see the water coming in, I guess, and the head of water over the filter, this is what you see, and then you see that the water will filter through it and come out here, let us say, right, will come out here, right. So, you have the filtered media and you have the under drains. Here this is called this kind of system typically will be a slow sand filter, because we are talking about what I always find difficult to pronounce, smudzuke, I guess, right. Again, you understand what I am referring to. What happens is over time this particular layer will be formed at the top of the sand layer. Okay. So, here what is happening, you have water with high organic content, either natural or due to human origins, organic content, let us say, organic matter. Whenever there is organic matter, you know that the microbes want to grow. So, you will have this mixture of microbes, organic content, and this cake being called, which you are going to refer as smudzuke, I guess. So, you will even have degradation of some of the organics, and you will have removal by straining. In this kind of slow sand filter, mostly the removal is by straining at the top layer and not by removal across the depth of the sand layer, But again, keep in mind that that's probably one of the reasons why it will be a slow sand filter where the rate of filtration is going to be relatively low, and also that is why rarely do people use slow sand filters, right. But again, you will have removal across the depth, but usually it's morely on the top, right, by straining. And how is it that people clean it? People clean it by either replacing or scraping off this layer from time to time, right. So that's something to keep in mind, but again, very rarely used. The MIT courseware says 50 out of 50,000, what do we say, filtration units in the US or such are slow sand filters. So that's something to keep in mind. But again, what's the principle here? You have media, and then you are going to have a layer developing over the top due to the screening action, and this layer will also have microbes developing there. So different kinds, obviously I think this is more or less okay. You can even have slow sand filters like this, but again we are moving into the zone of rapid sand filters and such. So this is a, what do we say, picture that will give us an idea about what we are looking at. So water coming in, and you see the gully or gullet, I guess, I think T is silent, yes, and you have next the filter media. You have the filter media here, right, and then the graded gravel, and after this the water has to be, or treated water has to be collected, and that's done through these under drain blocks. That's what you see out here, and that water obviously flows out through this main, yes, and that's the main aspect, I guess. These are the main aspects we have covered. But over time, let's say your head loss across the filter is going to decrease, not decrease, increase. So you have particles taking up the pore spaces, the pore size decreases. So over time, a lot of head is required to take the water through, and if it's pressured filter or pressured filtration, let's say, much more pressure is required, right. So think of this, water has to flow through this filter. So you can think of energy being lost or more energy being required. So head lost, right, head is being lost. So what do we do? People see to it that they backwash it. They pump water in the reverse direction, backwash, right, and then you are going to see to it that this particular filter is suspended, and then you are going to pump water out until these adsorbed what do we say, particles are going to be removed, and your filter media is relatively clean. So that's what you see, and once you do that, you have these wash troughs, right. So this is where the wastewater will be collected, let's say, right, because earlier this is the filter, but after you pump water in the reverse direction, the bed is going to expand, yes, and then this wastewater is going to be not wastewater, the high turbidity water, because you are washing your filter, is going to be collected in this wash troughs. I think we have a better picture here. Okay, this is what you have, actual one. So you have the filter box mentioned out here. This is the gully, and this is the filter cell, right. I think you can see the filter cell out here and the filter bed, and I guess the gully too, yes. And then backwash troughs, when it's pumped up, this will expand, right. You can see that it's expanded, or the bed is expanding now. Earlier water is coming in this direction, bed is in this thickness. During backwash, I am pumping it up, so bed is going to expand, right, and then that water during backwash will go through this backwash troughs, right. So that's something that you can see. We'll come back to more pictures later. So we were talking about sand or the media, and in general in your slow sand filters you will use or can use naturally occurring sand, and in the rapid sand filters or such where the rate of filtration is going to be relatively higher, you will typically use process filter sand. And what's the aspect that you can notice? You can see that naturally occurring sand, again keep in mind this y axis where you have the particle diameter is at logarithmic scale, and you see that the particle diameter, what do we say, ranges over a considerable or includes a different range of or variable considerable range of particle diameters, naturally occurring sand. But processed and filtered sand, you see that it is relatively more uniform, yes, that is something that you can see, right, that is something to keep in mind. And also here I guess it is percentage of media with smaller diameter, here it is relatively less, and here I guess the range is relatively more with respect to processed sand filter, right, that is something to keep in mind, or relatively uniform too, but it depends, I guess. Okay, so again different pictures out here. This is something that we already looked at, wash troughs, inlet main, and I guess you see this filter sand, graded gravel, filter sand, graded gravel, and then perforated pipes, because the water will then pass through these perforated pipes and go through the outlet. During backwash, obviously in the reverse direction, and this is going to lead to an expansion in your filter bed, and then that water will be removed through these wash troughs. And here at the bottom, what do we see? Here we had perforated pipes. You can also have vitrified clay blocks. So this is what they look like: gravel placed on top of block, and here you see the vitrified blocks through which your water is going to be collected here. And here I guess you have something called an IMS cap, right? Integrated media system, if I am not wrong. So here you see during filtration, the water will flow this way and then this way, right? And then this collected water, this is the side view, right? Or this is the section. So it will be collected here. During the backwash though, I am going to pump the water into this, and then it's going to clean this and move up through here, let's see, right? So that's what happens. Again, different kinds of what do we say, water collection mechanisms here, right? Perforated pipe, vitrified clay block, and then the IMS cap, let's see, right? Okay, filtration cycle. How is it that filtration is going to occur? Let's just look at that. So first I have to initiate operation. Because the filter is clean, there is nothing out there that will block the, or relatively less out there that will block my particles, or rather water. So there will be relatively less head loss, let's see, low head loss. And during this time, filter will start to ripen. Why do we say ripen? We have a figure later. In general, fruit, raw and ripe fruit, right? So ripe fruit is what you would prefer. We will also see why filter ripening is what you want. I think looking at the figure will help or understand this. So this will lead to increase in, or during this time, the performance efficiency of the filter will increase. Why is that? You have the particles coming in with the water. They are going to take up the pore sizes, right, or pore spaces, pardon me, and then you can have either flocculation or the pore sizes getting smaller. So that will lead to, in effect, relatively better filtration, right? So filter ripening. So continue operation. After filter ripening, you will continue operation. But for how long will you continue this operation? The head loss will increase. Over time, head loss will increase. The pore size or pores will be, what do we say, relatively smaller. And this will lead to head loss over time, increased head loss over time. And also second thing is, over time the performance efficiency of your filter will also decrease. So the turbidity in your outlet will also keep increasing. So you look at two factors when determining until how long is it you want to run the filter. You will look at the time it takes for your unacceptably level, a high level of head loss to be achieved, or time it takes for unacceptably high level of effluent turbidity to be reached. So that's what we look at. Head loss increases during that period and turbidity removal decreases. When am I going to stop operation? When the head loss is unacceptably high or turbidity is too high. We will choose the smaller of the two. And then after this, obviously I can't throw the filter out or the media out. What am I going to do? I am going to backwash to a clean filter. So hopefully I have this. Okay. What do we have here? We have two graphs, effluent turbidity on the y-axis and minutes on time, I guess, and or hours of filter run out here. So you see this in general filter ripening, so 30 minutes to maybe 2 hours typically, to 2 hours, yes. And here what do you see? Effluent turbidity initially high because of the pore sizes and relevant variation, but after the filter or during the filter ripening, obviously you can see that the filter efficiency increases considerably. This is within the first 30 minutes or 2 hours, right? The pore spaces are being taken up and you have more efficient filtration. After this 2 hours, over time it runs for pretty, this means a break in time. Obviously this is minutes and this is hours. So here you see that the efficiency is pretty good. The effluent turbidity is relatively low, right? The effluent turbidity is low. So what happens after a certain time though? Now your relevant turbidity starts increasing and then you are going to stop it, right? Time for this particular aspect can be noted. And in general, this period between ripening to run termination can be between 1 to 4 days. 1 to 4 days. Simultaneously, what will happen as your filter is being, if to use layman's terms, choked. So here time of filter run on the x-axis and on the y-axis head loss. So what's happening? Head loss is increasing and increasing. With clean bed, this is the head loss. Obviously, with clean bed too, you will always have head loss, but not much, depending on the uniformity coefficient and such. Head loss through the filter is going to keep on increasing, and at a particular time, you know, it's unacceptably high, so I am going to stop it. So, this is one particular time. So, I look at which time is smaller and then choose that time to backwash, let's say, right. Again, it depends upon if it's too odd, you will also, people will also set up regular backwashing cycles, but again, that has to look at the conditions on the site. So, with that, I will end today's session, and in the next session, we will look at the relevant aspects as in head loss, how do I design the relevant aspects and such. As usual, thanking you for your patience, I end this session.